Welcome to you from ChemHelp ASAP. In this video, we'll demonstrate a classic organic reaction, the SN2 reaction. Specifically, we'll do an SN2 on a primary bromide with the NH2 of an aniline. We will briefly discuss the reaction, perform the experiment, isolate the crude product, and characterize the material. Handouts for the lab procedure and NMR spectra are available through links in the video description. Here is a general depiction of an SN2 reaction. Note that we start with a nucleophile, typically a strong nucleophile, and that's this reagent in the middle. This is a molecule that has a lone pair. Almost always your strong nucleophile is going to have a negative charge. We're going to see an exception to that in our reaction today. And the lone pair, in one step, the lone pair simultaneously attacks the electrophilic carbon. At the same time, we break a bond from that carbon to a leaving group. That's typically a halide, but it could be something like a tosylate or a mesylate. And we will kick out our halide, which I haven't shown, or whatever our leaving group is. We lose our halide and we form a new bond to the nucleophile. As I said, this is a one-step process, and if we had stereochemistry at our electrophilic carbon, we would see inversion. In this case, we have a primary halide, and there is no stereochemistry to worry about. On the screen, we have the reaction scheme for our SN2 reaction for this experiment. So we have on the left, we have a primary halide, this primary bromide, and our nucleophile actually has a neutral nitrogen. This is not an anion. And this nitrogen, even though it's not an anion, is still nucleophilic enough to attack that carbon and kick out the bromide. So let's draw the actual product from that, because that's not going to quite make our final product. There we go. We're getting close. Now notice we had two hydrogens on our nitrogen, and those hydrogens are both still there. So what we get initially is this salt. Now the reaction is performed in a solvent, methanol, and we're going to have present a little bit of sodium bicarbonate. That's a very weak base. And the weak base comes into play in our last step. Here is bicarbonate. And our weak base is going to help deprotonate this extra hydrogen on nitrogen, and that's going to give us our final compound. So this is our SN2 product. To perform this reaction, we're going to use one equivalent of our halide, and we're going to try to match it as closely as we can with one equivalent of our nucleophile and see if we can just get this single SN2 product in high yield. So this is a fairly simple reaction to perform. Let's see how it plays out. Let's get started on this reaction. So the first step is to weigh out our reagents. And the first reagent I have here is 2-bromo-acetophenone. This has a molecular weight of about 199. Just for simplicity of math, I'm going to say it has a molecular weight of 200. So I want 5 millimoles of this reagent. So 5 times 200 gives us about a gram. So let's go ahead and tap this out. We're way low. It's about 200, 300, 4, 5, 6. Slow it down. And again, I don't care exactly what I get. Okay, that's overshot a little bit, but that's okay, because what I'll do is I do want to measure this out fairly precisely, and I want to get my stoichiometry as close as possible, as close as 1-to-1 as possible. So this is the amount I've overshot. Instead of about 1 gram, I have 1.074 grams. But that's all right. I'll go ahead and calculate the amount of para-toluidine I need based on this amount, so that I'll adjust that to this quantity. And we'll still be right at 1-to-1 equivalence, even though it won't be exactly 5 millimoles and 5 millimoles. So let's just go ahead and take this. I did not fold the corners. Typically I try to remember to fold the corners. It makes the paper just a little more rigid. And take that out. And now presumably we have 1.0 0.074 grams in this vial. And now we'll get ready I'll calculate the amount of para-toluidine I need, and we'll get as close as possible for that reagent. We're now ready to get our para-toluidine. So based on the amount of 2-bromoacetophenone that I used, I need 577 milligrams of para-toluidine. And this vial is not a very fancy vial. This is just a kind of a lab stash of this reagent that I use. No, para-toluidine is an aniline, and anilines tend to pick up a lot of brown color. And you might say, yuck, that looks terrible. Well, actually, it takes very little colored impurity to impart a lot of color. So even though this doesn't look very pretty, it'll be just fine for our reaction. So I need about 577 milligrams. This is going to take a little bit of delicacy because there's some big chunks in this bottle. Not too bad. That's about 500. And I want to get close, but I'm not going to obsess over being... Ooh, that's 567. That's not too bad. Get some more of these pieces. That's 5... Ooh, that is 578. 579 now. I will take that. That's pretty good. 579. I'm not going to do better than that if I try to mess around with it. Okay, so let's take that off. That's 579 milligrams. Now, while we're here, let's go ahead and get our sodium bicarbonate as well. Sodium bicarbonate, we need around 500 milligrams of this. I'm not as worried about getting this precise because this reagent is going to be easily washed away when we're done. So if we have a little excess, that's okay. We can rinse this away real easily. So that's 520 milligrams. That's close enough. We just want to be comfortably above 5 millimoles of that reagent. With a molecular weight of 84, we're fine. Okay, so there are our reagents. Let's now go to the hood and start putting these things together. Fantastic. So we are in the hood. Here is our vial. This is with our 2-bromoacetophenone. And I'm going to put in here small stir bar and 10 milliliters of methanol. So there's our reaction solvent. Lightly cap that because we're certainly not done. And we will have this stirring as it goes. So now we have to add our two other reagents. I'm going to go ahead and add the para-toluidine first. Slide that in there, nothing fancy. Let that stir. And then I'm going to add our sodium bicarbonate. Right there. That is a true dump and stir. And I will engage these threads, but I'm not going to screw them on tightly. Now, we're going to warm up this reaction. We're going to warm it up with a water bath. So here is the water bath. Note that it's fairly shallow. You need to be shallow because you don't want to float your vial. Now, I'm going to turn on the heat. Be careful with hot plates. If you notice, my bath is actually bigger than my hot plate surface. So if you turn up the hot plate too much, you basically have really intense heating over the ceramic top of the hot plate and no heating at all on this front edge and the side edges of the bath. And that thermal gradient, that high thermal gradient, can cause glassware to crack. Even though it may be Pyrex or heat-resistant glassware, you don't want to push your glassware too much because it'll make a mess and you got to reset up the reaction and you know, plus the glassware costs a little bit. So I'm just going to turn this on 1. All I want to do is warm up this methanol a little bit, and 1 on this water bath is plenty adequate, and a 1 on this hot plate is not going to get our hot plate too hot, so it's going to cause a problem. Sometimes people get impatient, it's like, I want it hot right now, and so I'll just crank it up to 10 for a few minutes, and then I'll knock it back down to where I want. And that's when you start to run into problems. So let things warm up slowly. I know it's hard to be patient, but it's a better approach than cleaning up a mess later. So let's just take a visual look. This is roughly dissolved. I think some of the bicarbonate is still in solution. It's a clear solution. Looks like it's kind of the brown color of the para-toluidine. And now we'll just let this stir. and warm up. And hopefully as the reaction goes, maybe we'll be able to observe some changes, physical changes in this reaction. This mixture has been heating now for about an hour. It's kind of hard to see with the bath in the way, but I'll take this out and you can see there is a lot of solid in there. There's still some dark color, but certainly we have a ton of precipitate. I had an old lab mate who would say color changes and precipitates are almost always a good sign in a reaction. I don't know if it's universally true, but it's a sign that something's happened. And if you designed your experiment to do what you want, then something happening means probably a good thing. So yes, color changes and precipitates are always exciting, and this definitely has a precipitate. So I'd say our next step is to take an aliquot out of that reaction and perform a TLC, and let's see if we actually have consumption of starter material and maybe some nice product spots. So that's the next step. Take a TLC. Well, here is our TLC plate from this reaction. I actually ran this as a 4-lane TLC plate. So I have one of the starter materials. Here's the bromine starter material, and there's a spot for that. And I had aniline, and there's our aniline, our para-toluidine. And then here are 2 different product lanes. This isn't a true 3-lane or 4-lane TLC. I spotted one lane a little higher concentration, the other lane a little lower. But these are both reaction lanes. And here's what we see. So it's not completely clear to me. So the mobile phase for this was 30% ethyl acetate, 70% hexane. Notice that the aniline, there might still be a little bit of aniline there, but it's basically gone. Now, what is not so clear is the bromoacetophenone. There could be some bromoacetophenone. Doesn't look like it perfectly lines up, but maybe there is. There are definitely, looks like multiple spots up here. So how do you interpret this? Well, if the aniline is gone, then our SN2 reaction is complete. Now, I can't totally explain these spots, but if the reaction is complete, we might as well end it. And what's encouraging is we do have these this precipitate in the reaction. So let's go ahead, based on this TLC plate, I think the next step is to stop the reaction, and I'm hopeful that that precipitate that we have in the reaction is our product. So let's go ahead and filter out that solid. Now to make sure we get as much solid as we can, I'm going to cool this down first. So we're going to put this on ice, and that should minimize the solubility of the product so that when we do filter it, we'll get a maximal amount of product as possible. So let's go ahead and move forward. I'll put this on ice, and then we'll come back and filter the cooled reaction. Well, let's go ahead and filter this material. So to do this, we have our filtration set up. We have a Buchner funnel, a rubber adapter to give us a good seal between the funnel and the sidearm flask, and the sidearm flask connects through this hose to our vacuum line. So let's go ahead, open that up. Now it's not going to come out, but one thing you can see, there is a filter paper in there. We want to make sure the filter paper is placed in so all the holes are covered. So we always have to seat the filter paper, and to seat the filter paper, we want to use whatever our primary solvent is that we're filtering. And so we're going to filter the reaction. The reaction's been cooling on ice, and so the reactions run in methanol. So we're going to use methanol to seat the filter paper. So don't think that, oh, I just always use water to seat the filter paper. You can't always use water. Only use water if you are filtering primarily a water mixture. And I'm looking in here, and all the holes are covered up. Okay, that looks great. Now let's go ahead. We have suction, and now I'm going to take this mixture and just dump all this in. That is thick with solid. Looks great. Look, a bunch of colored impurities are going through. And but now it's not as if what's in the top of the funnel is colorless, because it is not. Okay, and that's what we're going to do some rinsing for with cold methanol
Oops, I gotta hold this in front of the camera. Sometimes I get excited and I forget. This is so other people can watch, not just so I can do it. All right. Nice cold methanol. We'll swirl that around and dump that. And let's do a little more. This is a little bit tedious, I admit, but it's very satisfying. Now I got a little solid around the edges. Let's rinse that off with some methanol, so we can hopefully get every scrap of product that we can. And tell you what, why don't we just do this? That's a little more fun to see. Pour that through. And now, well, I don't have quite what I want here, but this is fine. I'm just going to pour this straight through. Looks good. Okay, that is drawn through. Fantastic. So this is filtered. All we've done is filtered our solid and rinsed it with, I wouldn't say exactly a minimal amount of methanol, but you know, we've got to use some, and we certainly used some, but not a whole bunch. And so now, hopefully, our impurities, which remain soluble, are down here. Looks like there's some solid residue. Wouldn't surprise me if we lost some product in that filtration. But we've got a pretty decent amount of solid in the top, and hopefully that solid is our material with as few impurities as possible. Of course, we won't know that until we take an NMR of this product, we take a melting point, and we take a TLC to analyze exactly what this solid is that we isolated up top here. So, I'll tell you what, before we cut off, let's go ahead and peek down in there. You can see it's got a little bit of a yellow tinge to it, not surprising, but that yellow tinge is certainly better than that deep orange color that we see in the bottom. So I think this looks pretty promising, but again, looking promising and being promising are two different things. So we'll just have to see what happens. So this solid has now been spread out on a watch glass and allowed to dry. I'm not sure if you can see, but you know, it is not 100% uniform in color. The edges tend to be a little lighter. In the middle, it's maybe a shade darker. That is, you know, when it was on the funnel, there were some thicker areas, and maybe those areas didn't get rinsed out quite as well. So our final mass is 995 milligrams, so not quite 1 gram, but pretty close, 995 milligrams. And so this looks like nice material. Now it's just a matter of, let's see how nice it is. Let's do some characterization. Get a melting point, a TLC, an NMR, and see if this is actually clean material, and determine what our final yield of our product is.
Okay, two forms of characterization, our TLC and melting point. So on the screen is our final TLC. Now this looks a whole lot better than that previous TLC. So our mobile phase is still 30% ethyl acetate, 70% hexanes. And we get a major spot that has an RF about 0.5, and then there is a faint spot in here. It's not pristine, and that has an RF of about 0.39 based on how I measured it. So I don't know what that lower spot is, but there's a little something in there, but this looks pretty nice. Now our melting point, on the other hand, is not quite so nice. This had a melting range. Remember, we say melting point, but people report melting ranges. About 125 to 130. Now this material, that's a pretty broad melting range, 5 degrees. Now if you go in the literature and look up this melting point of this compound, and this is a known material, it's not like this is uniquely made in this experiment. It has a melting point, you'll see 126, 128 to 129, so we're kind of in the right range. We just have such a broad range. So this is an indication that it's not that pure. Now, when you look at a TLC, you can say, well, it looks so good by TLC. Well, keep in mind, not everything shows up on a TLC plate, and sometimes spots can overlap. So just because you have one spot by TLC does not mean that your material is pure, but if it's not pure, then the NMR should tell the rest of the story. So let's get along and take a look at the NMR. Here is our full NMR spectrum. So here's our product shown on the left, and our NMR spectrum on the right. This NMR was performed in DMSO. So let's point out what the solvent peaks are. So this peak at close to 3.5 is water, and that's an impurity in our DMSO, so we don't have to interpret that peak. And DMSO itself gives rise to this small signal at about 2.5. So we don't need to worry about those two because those are part of the solvent that we use to actually acquire the NMR spectrum. Now, let's look at the rest of the spectrum, just a broad overview of the full spectrum. What I tend to look for in an NMR spectrum, I look for peaks that are kind of small because those are typically your impurities. And there are some small peaks that look like they're trying to hide, but they can't hide in the NMR spectrum. So this peak, that looks like an impurity. It's definitely there, but it seems disproportionately small compared to the other peaks. There's something going on the side of this peak that looks like it shouldn't be there. Now, as it turns out, this peak as well, it stands out a little bit more, but that is disproportionately small. This product has an impurity. I'll identify the impurity later. I don't want to go into full details. The purpose of this video is to show off an experiment, but I will make a separate video that will go into this analysis of this spectrum so we can try to identify what this compound is. I will identify it. I just don't want to go through all the long, gory details because maybe you're here just to see an experiment and see data gathered. But I think there is a time and place to talk about this spectrum. So let's go into this, but we know there are going to be some impurity peaks here. Here is the most downfield part of our NMR spectrum. So we're like in the 8 to close to 7 ppm range. And our product has a lot of hydrogens that are off a benzene ring. So there's no surprise that we see a lot of peaks in here. Now notice these integrations are roughly correct. This is roughly 2, and here's roughly 2, and 2, and 1, and 2. So these look pretty good. We do see these impurities in here, these troubling impurities, but we're going to focus on the main peaks in here. So this aniline ring has 4 hydrogens total. These 2 hydrogens by symmetry are the same. And those 2 are the same. Each of those hydrogens has 1 neighbor, so those should be doublets. This should be a 2-hydrogen doublet. That should be a 2-hydrogen doublet. And those are these 2 peaks right here. If I had to pick, I would say A corresponds to this signal and B corresponds to that signal. Okay, now let's look at the other aromatic ring in the molecule. These 2 hydrogens should be the same by symmetry. Each of those hydrogens has 1 neighbor. So this should be a doublet, a 2-hydrogen doublet. And let's label that C, and that's that 2-hydrogen doublet. These 2 hydrogens, and I'm running out of space on the slide, those 2 hydrogens each have 2 neighbors, and so they should be a triplet. It ought to be a 2-hydrogen triplet. And that's what we have here at about, what would you call that? 7.55 or so. And that leaves this single hydrogen off the end of the molecule. That has 2 neighbors. It should be a triplet. And that's what we have here. Let's label it. Say that's E. And that is E. So now we've assigned the aromatic region. That looks pretty good. It's not perfect. We have these impurities and there's other information here. But that looks pretty good. All right, so let's move a little bit more upfield. We're now around the 5 ppm range for this NMR spectrum, and we have 2 signals that show up in this range. We have these hydrogens that are off that CH2, and then we also have the NH. Now, I find this part of the spectrum kind of interesting. we have, typically in NMR, you'll find people often ignore OHs and NHs in terms of looking at neighbors and coupling. But we are performing this experiment, or this NMR spectrum, in DMSO. In DMSO, NHs and OHs do count as neighbors. So these two hydrogens, they have one neighbor. It's that NH. And so these should be a doublet. They should be a 2-hydrogen doublet. And that's exactly what we see. This is a 2-hydrogen doublet. So that's the CH2 group next to the carbonyl. Likewise, the NH should be 1 hydrogen, but it has 2 neighbors, the next door CH2. So this should be a triplet. It's 1 hydrogen, and that's exactly what we see. 1, and this is a 1 hydrogen. I'm sorry, it's not a singlet. It is a triplet. So that's great. And of course we have this troubling impurity peak on here, which we're going to skip, but that we can't ignore it. It's raising its hand, making itself known. But this is an interesting thing in DMSO. When you run spectra in DMSO, you will often be able to see coupling interactions between your NHs and OHs. In other solvents, the most common other solvent is CdCl3. You typically don't observe this type of coupling interaction between OHs and NHs. Well, there's not much left that we haven't discussed about this molecule. But the one thing that is left is this CH3 group. Now, we're looking now at the most upfield region. We already said at the opening that this is our water peak. That's not something we have to interpret. We said this is from some residual protium nuclei in our DMSO. We don't have to interpret that, but this is something we do need to interpret. Notice it's about 3 hydrogens. It's a 3-hydrogen singlet. That tells us that's a methyl group off of our aromatic ring. Now, if you look closely, and I almost covered it up with the circle, there is a little bump there. That's called a shoulder on a peak. And peaks with shoulders normally mean impurities. So there's our impurity. Keeps on rearing its ugly head as we work through this spectrum. But that is not the topic for this video. We're just trying to interpret and assign this spectrum of this product that we made. I said that I would identify at least what I think this impurity is. And so here are 3 compounds on the screen. Here is on the far left is the star of our show. That's our product, and by far the majority of what we see in our data reflects that molecule. I initially thought, based on the data in the NMR spectrum, that we probably had a little aniline. Our crude TLC from the reaction, when we stopped the reaction, I thought that showed some signs of having aniline in it, so I sort of was predisposed to think, it's going to have aniline. And then when I saw the NMR, I thought, yeah, that looks kind of like aniline, and didn't think about it too much. Then upon reflection, I think our final product, our final impurity, is actually this molecule on the far right. And what we see is our nucleophilic nitrogen has attacked the bromoacetophenone not just once, but twice. And that certainly can happen in SN2 reactions at times, especially with things like amines. So that is not a surprising impurity to see. Again, I'm not going to go into all the evidence, but I'll have a separate video that'll be linked in a card off of the screen where you can see that information if you're interested. Well, even though our material is not pure, we can go through the process of determining the percent yield. So we know for our starting bromide, we use 1.074 grams of material. This has a molecular weight of about 199 grams per mole, and that gives us about 5.4 millimoles of that reagent. Compared to the aniline, we used 0.579 grams, and this has a molecular weight of 107 grams per mole. That's our para-toluidine, and this has corresponds to a number of millimoles of 5.41 millimoles. So just about identical between those two reagents, although technically the bromoacetophenone is the limiting reagent. I won't go through the math on the bicarbonate, but we got a little bit of an excess of base in here. Has a molecular weight of 84. We use 520 milligrams, and that's a little over 6 millimoles. For our final product, we got 995 milligrams. This has a molecular weight of 211 grams per mole, and this corresponds to a number of millimoles of 4.72 millimoles. So our limiting reagent is the bromoacetophenone. That's our theoretical yield. If I can spell it, that's our theoretical yield. Okay, theoretical yield, and here is our actual yield of our product. So if we do actual divided by theoretical times 100, we get an 87% yield off this reaction. Now, I don't want to be a downer here, but it's not that pure. In fact, it's my best guess is probably 90% or a little less than 90% pure. Now, when you buy reagents typically from a chemical company, I'd say the standard for organic reagents is probably 98% or higher purity. Once you get down to like 95% purity, they typically call that a technical grade. It's not considered an analytically pure reagent. So, you know, we're well below 95%. We're sort of below a technical grade. So this is not a real high purity, but you know, at least we got a lot of not high purity. So anyway, it's a little bittersweet at the end, but that's our yield calculation for this experiment. That concludes this SN2 reaction between a primary halide and the nitrogen of an aniline derivative. Remember that handouts for the procedure and spectra are linked in the video description. Please subscribe, like, or leave a comment. Take care.